Hello everyone, welcome to the course on architectural design of ICs. So, in the last class we have discussed the basics of this FFT architecture, as why we have to know the FFT, the hardware architecture of FFT is that because FFT is one of the major mostly used block in digital signal processing. It has a wide application in for video processing, audio processing as well as image processing. All the DSP mainly uses, that means this first Fourier transform. So, that is why there are several works on this, that means developing the efficient first Fourier transform hardware architecture. So, we have seen that there are two type of architecture. One is this decimation in time, and another one is this decimation in frequency. Okay. So, in decimation in time, the inputs are in that means bit reversed manner, so that the output comes in the original sequence, whereas the in decimation in frequency we give the input in original sequence and we get the output in bit reversed manner. So, today we will see that okay, whenever we will use this butterfly unit. Okay. So, we have seen the data flow graph of the first Fourier transform. So, depending on that, all these butterfly unit actually now using one single butterfly, that means this is the serial implementation. That means, if we reuse one single butterfly to compute the whole FFT operations. So, because the butterfly unit is same, only the input at different stage, the inputs are different. Okay. Why? Because if I consider that okay, this 8-point FFT, so at that time it will be having log 2 base n number of stage. So, that means it will be having 3 stage. So, if we consider okay, that that if we are having this, let us say 16 point FFT. So, at that time the number of stage will be 4 whenever we are considering this butterfly of 2. That means, here we are using this radix 2 butterfly unit to compute the, that means the full first Fourier transform. So, whenever we will use one single butterfly or we will reuse the single butterfly unit to compute the whole FFT operation. So, at that time the computation time requirement will be much more higher, which makes the first Fourier transform very slow, whereas the area will be very much smaller, because only one single butterfly we are using. Okay. So, that the inputs are basically time multiplexed, but here actually the whenever we are doing this or we are reusing one single butterfly. So, at that time we need the controller should be designed in such a way, so that each of this, that means at what stage what will be the corresponding inputs to this particular node, that we have to consider very carefully. So, that is why the controller of this particular block, it will be much more complicated, whereas if we are having this fully spread, that means the parallel architecture, if we have just implemented. So, at that time speed wise it will be very fast. So, why that the computation time will be very fast, because all these particular operations are running in parallel. So, it depends upon the in one particular path. So, how many number of multiplication and additions we are that means doing, depending on that. So, that will be the critical path for this system. There I do not have to wait for that many clock cycles to what we have to wait for actually in case of serial implementation. So, area wise this will be much more larger than this serial implementation. Why? Because we are doing here, we are implementing in all this that butterfly in parallel. So, the controller is also very simple, because we do not have to, that means do the time multiplexing here, because all the inputs and all these intermediate signals are already available in this parallel case. So, that is why the controller is much more simpler than this iterative architecture or the serial architecture. So, whenever we are considering that means on the design perspective, so at that time the system requirement should be either speed, power or area. There will be trade off in these two cases, where actually for the parallel implementation we can basically increase the area, but the processing speed of the design processor, the FFT processor, that will be much more higher. So, which requires more number of processing elements, and this better processing elements utilization rate ratio as well as this better control scheme in case of, that means fully parallel design. So, but in case of serial implementation or this iterative implementation, so at that time there will be lesser number of processing elements required, but at the time of the utilization of these processing elements as well as this control scheme, that will be much more complicated. So, if we consider this one of this is the block diagram of FFT processors, which is basically runs in the this iterative mode. So, here we are having only one single processing element block, which is nothing but this butterfly operation. Then there we are having this coefficient ROM. Coefficient ROM means at what stage what will be the value of the twiddle factors. So, those values are stored in ROM, and then we are having this input buffers, and then we are having this first Fourier transform RAM. So, why I need this RAM is that to store the intermediate results, and that means for one stage whenever we will, that means compute all this, that means for the first stage, suppose for the first stage all the process butterfly operations has been done, then those computing values will be used for the next stage butterfly computation. So, at the time we have to save or we have to store those intermediate values somewhere. So, that is why we have to use the RAM to store the intermediate values, which process the that means this butterfly stage wise, and stage wise we also these coefficients are also different. So, that will also pass stored in a read only memory. So, that at every stage we, and who will basically control all these, that means what will be the input at what particular stage or for which butterfly, what will be the coefficient memory and where it will be again stored. So, everything is the job of this controller. So, that is why in iterative FFT processors this controller design is much more complicated than the this parallel implementation. So, the sum of the current architecture actually is that if we use this pipeline architecture, parallel, that means parallel of this along with this pipeline structure. So, here this is basically this structure is known as radix 2 multipath delay commutator. So, here you see we are having this coefficient, that means storage, then we are having these butterfly units. So, then again depending on this is fully parallel implementation. Okay. This is not serial, and if we that means what is the that means usefulness of this parallel implementation is that we can use the pipeline technique here. So, if we use the pipeline technique, so at that time the area requirement will be higher, but we can achieve a very high, that means operating frequency or the computation time for that particular process FFT processor will be much more lower. So, we have some of the application, like if we have to design this OFDM processor. Okay. So, in OFDM actually this transceiver we have to design, or we need the FFT and IFFT block which will be run in the gigahertz range. So, at that time we have to follow this particular architecture, where that means the area, if it is taking more area then it is no problem, but speed is my major concern. So, at that time we have to use this parallel, that means implementation along with the pipeline version of this. So, here you see that this is the radix to single path delay feedback. So, here only this butterfly, this 2 butterfly, basically it consists of 8, that means 8 times here, 4 times here, 2 times here and 1 times here. Okay. So, then again actually this is for a radix 4 single path delay feedback, which is been used for in, that means 256 point FFT. So, here you see we are having this butterfly unit of 4, which consists, that means which runs in the loop for 8 times, then again in the next stage it runs for the 4 times, and in the third it runs for the 2 times, and again it runs for the 1 times in the final stage. Okay. So, then the same thing, the radix for multipath delay commutator for this endpoint, that means 256 point FFT, they will be like, it has to consider this coefficient 4, and then this will be the butterfly unit 4, and then you have to multiply it with this 16, 32 and 42, then again something like this. So, this is the structure for radix for multipath delay commutator for 256 point FFT. And then again this another implementation of this radix for single path delay commutator for 256 point FFT is that here you see we are having this delay commutator of 6 into 64, then again it is going to this butterfly unit of 4. So, whenever we increase, that means for 256 point FFT, whenever we consider this butterfly unit of 2, so at that time how many stage we will having, that is log 2 base n. So, 2 to the power 256 means that is 2 to the power 8. So, 8 stage we have to consider, but if we increase the radix to 4, so at that time the number of stage requirement will be log 4 base 256. So, log base 256 means at that time the number of stage requirement will be divided by 2. Okay. So, but in case of this parallel implementation, we can, this is also, that means this parallel, that means this is nothing but serial here along with the parallel. Okay. That means it is not that some of this butterfly unit in each stage they are basically running in serial, but all of these are running in parallel. So, this is the mixture structure of serial as well as the parallel. Okay. So, this is the actually according to the that means the FFT architecture, what we have discussed is that whenever we will use more radix or the serial implementation, at that time the number of processing elements will be, or the area requirement will be lower, but the computation time will be slower. But whenever we will put more number of processing elements, more number of area, so at that time the processing speed will be, the computation time or the speed of operation of the computation of the FFT processor, that will be on the higher side. But here we are, so these two trade off, if we can implement or if we can design one circuit where this sum of the portion is serial and sum of the portion is parallel. So, that will give me the, that means that requirement for the processing elements will be 4 in this case, but the time requirement will be like as it is running for 8 times, this is running for 4 times, this is running for 2 times, this is running for 1 times. So, it has to wait for, so 8 plus 4 plus 2 plus 1, so a total 15 number of cycles to compute the whole task. Okay. But in case of only serial implementation, it has to run for, that means this has to run for log 4 base 2 to the power 56. So, the distinctive merit of this above is that the delay feedbacks are more efficient than the delay commutator in terms of memory utilization, and the radix for that means FFT has higher multiplier utilization, however, radix 2 has simpler butterfly which are better utilized. Okay. So, if we compare this in terms of radix along with the speed, if we increase, that means the radix, so at that time the speed will be higher, and if we decrease the that means radix, so at that time speed will be on the lower. So, the control part, if we increase the radix, so at that time it needs, or it will be, that means if we increase the radix, so at that time the control part will be much more complicated, and if we decrease the radix, so at that time it will be much more simpler. So, the processing ability or the processing elements, if we increase the radix, so at that time it will be higher. If we increase the that means if we decrease the radix, so at that time the processing elements requirement will be lower. So, combine the advantage for the decompose using high radix processing elements. So, how we can decompose the FFT for a better utilization or for designing one better FFT architecture. So, suppose here we are having this 4 of this multiplier and then the addition operation. So, we will just reuse this addition operation, the multiplication operations are in parallel, but we will use this addition operation, reuse the addition operation. Okay. So, then again actually we can decompose in another method, like we can consider, that means 3 different part where we can process k 1, then 2 k 2 and then 4 k 3, where this n 1, n 2 is 0 1 and n 3 is 0 to n divided by 4 minus 1. Okay. So, this is as we have considered these 3 index values. So, then again there are actually this particular actually method is known as this decomposition method, where this based on this actually we can compute the first butterfly 1, then again combination of this butterfly 1s, now I can make this butterfly 2 unit. Okay. So, what will be the corresponding structure of this is that, so suppose here we are doing this. So, here the first stage is the butterfly unit 1 and the second stage is the butterfly unit 2. So, instead of actually if we use this kind of that means this decomposition, so at that time this there will be one single, that means the trivial multiplication with the corresponding minus 1 term for the imaginary part. Okay. So, then actually this butterfly unit 4 you can just decompose it into butterfly unit 2 1 and butterfly unit 2, which consists of 2 butterfly 1 unit. Okay. So, this is the corresponding structure of butterfly 2 unit, where it takes 4 of this x n, then sorry, this is the real n, this is imaginary, and this is the real n plus n by 2, where this is the imaginary n plus n by 2, and it produce the z n plus real of n plus n by 2, z imaginary of n plus n by 2, and z real of n, z imaginary of n. Okay. So, this is the BF2 architecture, this is BF2, this is BF1 architecture, this is BF2 architecture, and combination of them, now I can implement this is radix 2 square single path delay feedback architecture. Okay. So, where we have this BF2 I and then we have this BF2 2 I, considering the above decomposition what we have already used or in the equation we have shown earlier. So, here for actually in this particular case we have to, this is for 256 point FFT. So, in this case we have to run it for 128 times, then again in 2 we have to run it for 64 times, then in the next it will be run for 32, here it will be run for 16. So, all these are basically running in parallel. Okay. So, the original actually the architecture for this 256 point FFT which we have already discussed is that it was butterfly unit of 4, it has to run for 8 times. This butterfly in the next stage the butterfly unit 4 has to run for 4 times, then the butterfly unit 4 has to run for 2 times in the third stage, and in the final stage is it has to run for 1 number of iteration. Okay. So, this is this particular, this is the newer actually architecture for implementing the n equals to that means 256 point FFT. So, here what is the problem is that as we are considering this 4 butterfly radix 4 butterfly. So, at that time the processing element requirements and the controller part will be much more complicated, but in this case it will be much more simpler to implement. So, the structure advantage is that the radix 2 has same complexity as radix 2 square has the same complexity as radix 4, but still retains radix 2 butterfly structure. The stage has non-trivial multiplication, the control is also very much simple. So, that the synchronization in the controller and the address counter for this W n. Okay. So, that is why in this case the controller as we are considering this butterfly, that means radix 4 butterfly unit. So, that is why the design that the controller design for this kind of architecture will be much more complicated than the this one, as we are considering only radix 2 butterfly unit. So, then again this is the actually structure for radix 4 multipath delay commutator block. Then we are having this radix 4 single path delay commutator block. So, here you see as we are having this multipath means we are combining 4 of the paths. So, here this is single path means only one single path is basically the multiplication operation is performing after this butterfly by only one. So, all this here parallel implementation means actually here also we are following this radix 4, but the hardware requirement for this particular case will be much more higher than this one. So, then again actually if we consider this radix 2 single path delay feedback. So, as we know that in DIT it will be in bit reverse to normal, but in decimation in frequency it will be normal to the bit reversed. So, then again actually if we consider this radix 2 butterfly unit for computation of 16 point FFT. So, at that time the input will be something will be come to the first stage, and then this radix 2 butterfly has to run for 8 times. Then the twiddle factor will be multiplied with each of this that unit which will be produced from this butterfly operation. Then again it has to in the second stage it has to run for 4 times, in the third stage it has to run for 2 times, and in the that means final it has to run for 1 times. Okay. So, this is the basic butterfly structure what we use in this particular processing as the processing element. So, in case of this radix 4 single path delay feedback. So, this is radix 4 butterfly, then we have to run it for n by 4 times here n by 16 for the next stage, and the final one has to run for only single one. So, here we require log for n minus 1 number of multipliers for this complex multiplication. So, the ideal architecture for is that whether I need the minimum number of that means the FFT architecture, which will require the minimum number of memory size for storing the that means the coefficient as well as the intermediate values, the minimum number of adder requirement as well as the minimum number of multipliers requirement. So, that is why people are basically trying to develop this FFT architecture considering all these aspects. And what I say is that when the processing elements, we increase the radix, and the processing elements if we use, at the time the controller will become much more complicated. At the time the memory size, either this will increase the memory size or it will increase the corresponding this multiplier requirement and the addition requirement. So, we have to develop one FFT processors which will be much more, that means enhanced, or which can use minimum number of this resources as well as minimum number of memory to get the advantage in terms of speed, in terms of power and in terms of area. Okay. So, there is another actually this new FFT processor, which is this radix 2 square, that means, and we can also, this is not only that you can do this radix 2, radix 4, you can also implement radix 8 algorithm for, that means FFT. For this video processing, we need the FFT processors of, let us say 8192 point FFT. So, at that time using radix 2 butterfly unit, it consumes too much of cycles to compute the full task. So, at that time we have to consider this we have to consider more number of radix for the processing elements. You also can do one thing, that is mixed radix architecture is also there. That means, some of the parts you can that means compute using, that means the first stage you can compute using radix 8, the second stage you can compute using radix 4, the third stage you can use of radix 2. So, mixed radix architecture is also there to gain the benefit in terms of low area, as well as that means the control circuit becomes much more that means less simpler, as well as you can get or the processing speed in a reasonably higher than the, that means if instead of using only radix 2 butterfly unit. Okay. So, this is one of this that means newer FFT processors where we use this radix 2 square, and this is the equation how we that means derive from these equations, and then it has to implement like this. So, this is the radix 2 square implementation we have already said. So, in radix 2 square we are having this butterfly unit 1 and then we have the butterfly unit of 2. So, here the intermediate results are being stored and then again it runs in serially. So, this is the hardware comparison of different that means, this is radix 2 multipath delay commutator block. So, the multiplier requirement is this, memory size requirement is this, and the adders, that means requirements this is radix 2 single delay feedback. So, this is radix 2 square single delay feedback. So, here you see the minimum number of, that means multiplier requirement corresponds to radix 4 single delay feedback, radix 2 square single delay feedback. So, all are basically log 4 base n minus 1, whereas the memory size for this radix 2 single delay format single delay feedback and this radix 4 single delay feedback is n minus 1 n minus 1. This radix 2 square is single delay feedback is also the memory requirement is n minus 1, and that means the adder requirement is 4 log 4 base n. So, if you compare this hardware requirement for this different architecture, you find that the radix 2 square single delay feedback architecture is basically having the advantage in terms of multiplier requirement, the memory size requirement and the adder requirement. So, this is the recent day that means FFT architecture which people have already developed, but it is not that this is the ultimate one, still people are trying to use or trying to develop the newer architecture for FFT. Okay. So, this is the simulation results, that means you can just write the code in MATLAB and then you can write, as well as you can just do this hardware implementation and then you can run the, that means that how much that means in whenever you are running in MATLAB. So, at the time it is running in the floating point environment, whenever you are running in hardware. So, at the time this is fixed point environment. So, depending on this truncation or this overflow. So, what error or what is the difference between the that actual FFT implementation you are getting in terms of MATLAB or the actual that means implementation you are getting in terms of FFT hardware. So, this is the simulation results, and if you just compare this error. So, at that time in MATLAB, actually in compare with the MATLAB FFT, the error in real part, that is in 10 to the power minus 4, and in case of imaginary part, that is also in the power of 10 to the power minus 4. Okay. So, whenever we do this FFT architecture, at that time initially we have to fix that what should be its bit, that means word length, so that this particular error becomes that okay, it will be much more on the lower side. So, we initially we have to run the algorithm on the MATLAB to fix all these values, and then we can go for the hardware implementation using different kind of architecture. And the ultimate target for designing this hardware for FFT is that we have to use minimum number of multiplier, minimum number of memory requirement, memory storage requirement, and minimum number of addition operations, okay, which will gives me the benefit in terms of speed, power and area. So, this is it for the FFT architecture. If you need to know more, then please go through Google Scholars, find the latest architecture on FFT, or if you need more information, then please let me know via discussion forum. I will provide you the more information about the recent days FFT architecture for VLSI implementation. So, thank you.